Now, one thing that needs to be mentioned is the comparison between velocities in this frame and velocities in this frame. The drone is moving this way, meaning that as it sees things, anything that we see at a fixed position is moving toward its x-axis, assuming that that thing is above its x-axis, on this side of its x-axis. It's going to be moving toward the x-axis. The distance between the x-axis and the object in this situation is going to be decreasing. The object will be moving in the direction opposite. In the drone frame, the object will be seen to be moving in the direction opposite that of the drone frame. At least a stationary object would be so observed. Okay? So, example. If we're sitting beside the road and a car is approaching us at some speed, then that car perceives us as getting closer and closer to it. So it's moving, the car is moving in the positive direction, but as seen from that car, we're moving toward it in the negative direction. Okay, so there's a generalization of that, and you really need to think through this in detail, that v prime, the vector velocity as measured from the drone frame, is equal to the velocity in the original frame minus the velocity of the reference frame. Okay, its velocity as observed from our frame. Now your book gives you subscript rules and all sorts of things, but you really need to be able to visualize this and make sense of it, and make sense of this relationship. And this relationship is always going to hold. There are qualifiers. Okay, this is the velocity of the new reference frame in our frame. It's got to be subtracted from the velocity of whatever's moving in our frame to get the velocity as observed from the reference frame. Okay. Now, on a simple level, these objects are both moving in the x direction, and the reference frame is not moving in the x direction. So the x components of the velocity in this frame will be the same as the x components of the velocity in the drone frame. So that v1 prime, and the prime meaning velocity in that new reference frame, is still going to have component 4 meters per second times I, the same as what it had. And this is going to have negative 2 meter per second times I x component. They'll each have a y component though. Now neither one of them has any velocity in the y direction, so that the y velocity of each as observed from the reference frame is going to be equal to the negative of the velocity of the reference frame. So the y velocities of both of these objects will be observed to be negative 3 meters per second times j. Okay? So v1 prime is going to be 4 meters per second times I minus 3 meters per second times j. v2 prime negative 2 meters per second times I minus 3 meters per second times j. And of course, if we take our 4 meters per second times I and subtract the velocity of the reference frame, and that would give us a negative 3 meters per second times j, this is exactly what we'll get for v1 prime, and this is exactly what we'll get for v2 prime. Okay, now the after collision velocities are what? Well, the velocities reverse in this frame, and we still have the negative 3 meters per second times j, because the reference frame is still moving in this direction, observing things that are not moving in the original y direction as moving in the negative y direction. So u1 prime and u2 prime, either using this formula or reasoning it out, and you should be able to do both, are these. Now, we didn't work it out, and I'm not going to work it out here because it's really easy to work out. You should verify that m1v1 plus m2v1 prime plus m2v2 prime equals m1u1 prime plus m2u2 prime. In other words, that kinetic energy, that momentum is conserved in the drone frame. So just plug in this expression for V1 prime, this expression for V2 prime, this expression for U1 prime, this expression for U2 prime. All the I components will come out to be equal, all the J components will come out to be equal, and you will verify conservation of momentum and conservation of kinetic energy. Okay? Take the speed, the V1 prime, the magnitude of this velocity V1, and in this case, 4 squared and 3 squared makes 25, square root of which is 5. V1 is just going to be 5 meters per second. V2 is going to be what? Square root of 13 meters per second. But we're getting to square those, so we don't have to worry about the square roots. V1 prime squared is going to be 4 squared plus 3 squared, meters squared per second squared, 25 meters squared per second squared. 2 squared and 3 squared is 13. So we're going to have 1/2 m1 times 25 meters squared per second squared, and 1/2 m2 times 13 meters squared per second squared. That's for our V1 and V2. And then our U1 and U2, well, they're going to come out exactly the same. And we'll verify conservation of kinetic energy. Now, if you're given an elastic collision, you can always find its center of mass frame and apply these ideas of moving frames or relative motion between reference frames. And once you're in the center of mass frame, whatever your velocities are in that frame, they're going to reverse on the collision. That's going to conserve momentum, it's going to conserve kinetic energy. And then if you want to get back into your original frame, just go back into your original frame. Just think through how that would work. I'm not going to go through the details, but I will tell you how to get the center of mass frame, the velocity of the center of mass frame relative to our original frame.